Blasius' analysis focuses on the laminar boundary layer forming on a flat plate. The main aspect of his work is the transformation of the partial differential equations for a flat plate boundary layer with zero pressure gradient into a single ordinary differential equation using a coordinate transformation. We assume that the properties of the fluid are known, and so the Reynolds number. Blasius used the stream function to describe the two-dimensional flow. This function automatically satisfied the continuity equation by definition. The coordinate transformation is performed introducing a non-dimensional coordinate for the y direction normal to the wall, and it's defined as eta and based on the boundary layer thickness correlation with x. We can then define a scaled form of the stream function based on the dependent variable function f of eta. With this in mind, we can see that the stream function is proportional to the function f. The velocity components are proportional to the first derivative of f, and the second and third derivatives of f are proportional to the first and second derivatives of the velocity. Note that the prime superscript represents the derivative of f with respect to eta. Substituting these relations into the momentum equation, we get the final form of the Blasius boundary layer equation for a flat plate. This equation can be solved on set the appropriate boundary conditions that, for our case, are f equal to 0 at the wall because the wall forms a streamline, the first derivative at the wall equal to 0 to impose the no-slip condition, and then the first derivative of f equal to 1 as eta goes to infinity to have the velocity equal to the free stream velocity outside the boundary layer. Blasius solved this equation using an analytical series solution technique. Nowadays, thanks to the availability of computers, we can obtain a numerical solution of this equation and calculate it with high degrees of accuracy. In order to do so, we need to cast the Blasius equation as a set of coupled first-order ODEs. Welcome to the bonus content of this lecture. Here, I'm going to explain how we can solve numerically the Blasius equation. A possible method is to use the shooting algorithm to find what value of h will satisfy the boundary condition at infinity. The first step is to guess a value of h at the wall. Then we solve the ODEs marching along the non-dimensional coordinate until the first derivative of f stops changing. Next, we check if our first derivative satisfies the boundary condition. If it doesn't, we can adjust the h value, either decreasing it or increasing it, if the first derivative is higher or lower than 1, respectively. The algorithm is repeated until the boundary condition is finally satisfied and we reached our solution. Reported here is a tabular form of the values of f and its derivatives, and as you can see, the solution is a value of the second derivatives of f at the wall equal to 0.332. On the right is a plot of f prime versus the non-dimensional coordinate. This is directly a representation of the velocity profile inside the boundary layer. Once the solution is obtained, we can calculate the velocity components using these relations. Hence, we can calculate the boundary layer thickness locating the point where the velocity is 99% of the free stream velocity. That occurs at approximately eta equal to 5. Using the solution, we can also estimate the displacement thickness and momentum thickness. The two terms can be rewritten in these forms. Last, we can estimate the wall shear stress based on the velocity gradient at the wall and calculate then the friction and the drag coefficient. Note that the expression is only accounting for one side of the plate. It is interesting to compare the exact solution with the approximate solution from the integral analysis. The relations are pretty close to each other. Indeed, the integral analysis is within 10% of the exact solution, but unlike the Blasius solution, these values were obtained without any complicated math. The Blasius solution provides a self-similar solution, meaning that the solution is the same if the independent and dependent variables of the governing equations are appropriately scaled. This can be seen in the comparison of experimental results with the Blasius solution. Different Reynolds number provide the same profile when the variables on the two axes are scaled properly.